When a brand new computer powers on and connects to a network port, it exists in absolute isolation. It has no address, no identity, and no ability to communicate. A single electron pulse fires into the darkness of the cable, searching for a network it cannot yet speak to. This creates a strict engineering problem known as the identity paradox. For a computer to request an IP address from a server, it needs an IP address to send the request. You cannot make a phone call to request a phone number if you do not have a phone. Before automation, network administrators solved this by physically walking to every single machine. They manually typed in the IP address, the subnet mask, and the gateway for each computer, recording every assignment in a physical ledger. In an enterprise environment with thousands of machines, this manual configuration was slow, error-prone, and entirely unscalable. The solution to this bottleneck was the Dynamic Host Configuration Protocol, or DHCP. It is a four-step automated negotiation process that network engineers refer to as DORA: discover, offer, request, and acknowledge. To bypass the paradox, the completely unaddressed machine constructs a DHCP discover message and fires it at a universal broadcast address. Instead of routing the packet to a specific server, the switch forces a copy of that shout to every single device on the local network simultaneously. The printers and laptops ignore it, but the designated DHCP server hears it and begins the assignment process. This automation replaced rigid, human-managed ledgers with a system that handles its own allocation. Addresses are now leased, used, and recycled automatically, allowing networks to scale to thousands of devices without a corresponding increase in administrative burden. This animated diagram shows a cylindrical cross-section of a DHCP offer packet in flight. The outer shell is the standard IP routing header, but the actual identity grant sits deep inside the inner DHCP payload. Inside that payload, the field for the client's current IP starts completely blank. Directly below it, the Your IP field carries the new address the server is offering to the isolated machine. But an IP address alone is insufficient. The options band at the base of the packet uses a type length value format to pack in the remaining context. In one single delivery, the machine receives its subnet mask, its default gateway, its DNS server, and the exact expiration time of its lease. Yet this highly efficient automated process contains zero native authentication. A DHCP client simply broadcasts a request and blindly trusts the first response it receives. An attacker on the local network can listen for these discover broadcasts and deploy a rogue DHCP server. By racing the legitimate server to respond, the attacker can offer the victim a fake gateway address. The victim accepts the configuration, and all of their outbound traffic is silently routed straight through the attacker's machine. Network engineers defend against this using DHCP snooping. The switch is configured to recognize which physical hardware ports are trusted. If a DHCP offer originates from an untrusted port, the hardware filter drops the packet instantly, severing the attack before it reaches the client. Once secured and configured, the machine has its logical identity. But a logical IP address only tells the network where a machine belongs. It provides absolutely no instructions on how to physically move an electron across a local copper wire. When a computer wants to request a web page, it knows the destination IP address. But IP addresses operate at layer 3, the logical routing level. The local network hardware operates at layer 2, which requires a physical hardware address to successfully construct an Ethernet frame. That physical identity is the MAC address. It is a permanent hexadecimal code burned into the silicon of the network interface card at the factory. This two-layer diagram visualizes the divide. The machine knows the IP address hovering on the top layer, but it means the specific hardware MAC address resting on the bottom layer to actually transmit data. The Address Resolution Protocol, or ARP, bridges this gap. The sending machine blasts an ARP request across the entire local subnet, essentially shouting, "Who has this IP address? Send me your physical hardware address." Every machine inspects the request, but only the node holding that specific IP address replies. It sends a direct, unicast message back to the requester containing its exact MAC address, allowing the physical Ethernet frame to be fully assembled and sent. ARP is extremely fast because it is mechanically simple, consisting of just two small packets.
But this efficiency comes with a trade-off. The protocol has no built-in way to verify the information it receives. To prevent shouting across the network for every single packet, machines store the results of these requests in an ARP cache, a temporary local memory bank mapping IP addresses directly to MAC addresses. The protocol's critical vulnerability is that it is stateless. A machine will accept and log any ARP reply it receives, even if it never broadcast a request in the first place. In an ARP cache poisoning attack, a malicious device injects its own MAC address into the victim's cache, overwriting the legitimate entry for the gateway. The victim's computer continues to send data to the correct IP address, but because the physical MAC address was altered, the traffic flows directly into the attacker's hands. Because ARP attacks exploit the local physical wire, stopping them requires dynamic ARP inspection. This security feature cross-references every ARP packet against the secure binding tables built earlier by DHCP, dropping any physical address claim that contradicts the established logical record. The security vulnerabilities of ARP are so ingrained in its architecture that modern IPv6 networks have abandoned the protocol entirely, replacing it with the cryptographically verifiable Neighbor Discovery Protocol. ARP successfully maps the local physical wire, but if a packet leaves that wire, travels across the country, and vanishes into a dead routing end, ARP provides no feedback to the sender. When a packet hits a dead end deep in the internet, the traditional default response is a silent drop. The sender receives no error report. It simply sits in the void, waiting indefinitely for a response that will never arrive. The Internet Control Message Protocol, or ICMP, was engineered to solve this silence. It acts as the network's diagnostic nervous system. Looking at this cross-section of an ICMP packet, the payload is dominated by the type and code bytes. A Type 8 packet is an echo request, and a Type 0 is an echo reply. Together, these form the foundation of ping, the most universally used connectivity test in networking. If that type field flips to 11, it signals time exceeded. Every packet has a time-to-live countdown to prevent infinite routing loops. When that counter hits 0, the router drops the data and fires an ICMP Type 11 back to the sender. The traceroute tool exploits this exact mechanism, deliberately expiring packets to map the exact physical path through a network. ICMP also regulates data size through path MTU discovery. If a restrictive network link cannot handle a large payload, the router drops it and returns an ICMP Type 3 message, instructing the sender to fragment the data into smaller, digestible pieces. Without this continuous, automated error reporting, the global internet would be an untroubleshootable black box. Because ICMP provides direct communication to operating systems, it has been heavily weaponized. Historically, attackers crafted massive ping-of-death packets to crash system buffers, or spoofed broadcast addresses to trigger Smurf attacks, amplifying a single ping into a crushing avalanche of replies. Today, attackers use ICMP tunneling. Because standard firewalls often allow basic diagnostic ping traffic, hackers strip out the standard ICMP payload and replace it with malicious, smuggled data, bypassing security checkpoints entirely. This creates a filtering paradox for network engineers. Blocking all ICMP strictly secures the perimeter from tunneling attacks, but doing so catastrophically breaks path MTU discovery and routing diagnostics, causing legitimate connections to silently fail. This tension is managed constantly at a massive global scale. Every single time you request a web page, DHCP grants the identity, ARP maps the local wire, and ICMP monitors the routing health. It requires thousands of invisible exchanges, choreographing in milliseconds. This split-second automated communication secures financial markets, routes global logistics, and supports life-critical telemetry in hospital networks. These three protocols form the fundamental cycle of every connection. DHCP provides identity, ARP finds the path, and ICMP reports if the road is blocked. Together, they turn a collection of isolated hardware into a functioning global network.